This screencast describes the relationship between the velocity potential and the stream function, and also shows that the velocity potential that we are working with is possible. So let's start with our velocity potential, which equals 3xy squared minus x cubed. And what we want to find out is the stream function. So what relates the two of them? What relates them is u and v, because u can be found by taking the derivative of this velocity potential with respect to x, which equals 3y squared minus 3x squared. Our v can be found by taking the derivative of the velocity potential with respect to y, and that equals 6xy. So what do these have to do with the stream function? Well, the stream function, the derivative of the stream function with respect to y actually equals u, which is 3y squared minus 3x squared. So we can separate this and integrate it such that d of the stream function equals 3y squared minus 3x squared dy. And when we solve this, we find that the stream function can be written as y cubed minus 3x squared y plus some function of x. So this is only part of the stream function. The next part is with respect to x, which equals v, which equals 6xy. And so we do the exact same thing, separate and integrate, but now this is with respect to x, and when we solve for that stream function, we end up with minus 3x squared y plus some function of y. By the way, this should be minus, which is why this is negative and this is negative. So now let's put our answers together, and what we end up with is a stream function that is y cubed minus 3x squared y, which appears in both of our two equations for the stream function, plus some c, which at this point we're going to call 0. Now that we've figured that out, let's go back and see if this velocity potential is possible. So there are two ways to figure that out. Either it has rotation, and if it has rotation, you cannot have a velocity potential. So let's check the rotation. So this is 1/2 dv dx minus du dy. And this has to equal 0 in order for this to be a valid velocity potential. So this equals 1/2 6y minus 6y, which equals 0. The second thing that we can do is take the Laplacian of the velocity potential. So we take the second derivative of the velocity potential with respect to x, add it to the second derivative of the velocity potential with respect to y, and ask, does that equal 0? So our second derivative with respect to x equals minus 6x. Our second derivative with respect to y equals 6x. And when you add them together, you get 0. By the way, the easiest way to do this Laplacian is to go back to your definitions of u and v, which is the first derivative of the velocity potential with respect to x and the first derivative with respect to y.